Hello and welcome back to Calculus 3. We are starting chapter 14 and this one will be on vector calculus. The first lecture is on vector valued functions. So in order for us to do calculus in three-dimensional environment, we need to define a vector valued function which will be, let's say, tracing the motion of a flying bug or a bird, or the car driving through a mountain road, goes up and down, left and right, all over the place. Think of a tuna swimming in the sea all over the place, right? So we are no longer limited, only going left and right, up and down. Now we have 3 degrees of freedom, which are 6 directions, and all of them combine together to give us these complex paths in 3D. So if I have, why is this blue now? So if I have in my XYZ coordinate plane, if I have some kind of a curve, we can trace a point XYZ using this vector. And this vector will be the position vector R, which will have 3 functions to create the coordinates of each point that it traces. Function f of x, function f of t, g of t, or h of t, which will eventually give us x, y, and z components. Now, in literature, they use either f, g, and h, or they use x of t, y of t, and z of t. And that, if you remember, was your what? Parametric set, right? Yes. So this vector R is nothing but the vector of parametric equations. We call that vector valued function. And now we're just, instead of writing all of those equations separately, we are going to write all of those equations in one vector and call that vector R. So we can call it position vector, but we'll call it vector valued function. So vector valued function R of t, and I'll use x of t, y of t, z of t to emphasize that calculating this vector, you are getting those points which are locations in xy plane. So if my vector R of t is given as 3t minus 1, e to the t, and 1 over t, we can calculate location R of 0, which would be -1. Can't do 0 because of 1 over t. Who put that 1 over t there? How about 2? Problem solved. So that's 5 e squared and 1/2. Now, that's a vector. with a terminal point five e squared 1/2. E squared is about 10, so please don't panic. So vector valued function is nothing else but the collection of all of these guys. Vector valued function r of t can also be represented as x of t I plus y of t j plus z of t k if you want to use component form. Every time when you compute vector valued function, you will get a vector whose terminal point is the point where the object is, where the bug is, where the bird is, whatever you are tracing in space. Straight lines, which we studied last class, can be represented through vector valued function in 3D. So I can have a point A at 1, 6, -2, point B at 3, 3, and 1, whatever. And we can use what we learned the last class to come up with the equation. So if we put this point to be the fixed point, we will calculate our vector v, which is our third-dimensional slope, as 3 minus 1, 3 minus 6, and 1 plus 2, which would give us a vector 2, -3, 3. And then we would come up with our parametrization x, y, z using our fixed point 1, 6, -2 plus 2t minus 3t plus 3t using vector v. But now we have a way to combine all of that in a single vector, and that's going to be 1 plus 2t, 6 minus 3t, -2 plus 3t in a vector. If something is moving in a straight line through space, we can find its location if you provide parameter t. That parameter t could be time. So where is this object after 2 seconds? Where is the object? Well, it's simply r of 2. Plug in 2. The vector would be 5, 0, 4, and the location would be 0.504. And we know the way to graph that, right, by counting 5 down the x-axis, 0, and then going strictly up. So if we want to graph this, we would count 1, 2, 3, 4, 5 to get our 5, 0, 0 location. And then since y is 0, we are not going to go parallel to y-axis. We're just going to go straight up 1, 2, 3, 4 units to get to 504. So 504 is above x-axis as a location. So there is this that will be a 4 on z. So that's where the object is at t equals to 2. You can calculate for, let's say, t equals to 3. And for t equals to 3, we have vector r of 3 to be given as 7, negative 3, and 7. Right? 3 times 3 is 9, minus 2 is 7, and then that's a 6 plus 1 is 7 as well, and then 6 minus 9 is negative 3. Great. So now for this one, we would figure out where 7 is on x-axis. Then we would go negative 3 on y, which would push us more this way, and then 7 units up. 2, 3, 4, 5, 6, 7. So this point here would be 7, negative 3 on y, 7. And then you can join these 2 points with a straight line, because we did talk about straight line if you want to, right? To get your line L. So we found 2 locations in space. We found 2 locations in space, and we just connect those 2 with a straight line, because we were talking about straight line. But not every path is a straight line. We talked about the helix at one point in time. So the best thing is to draw the helix first, and then to just fit in the axis. Helix. It's a spring in your pens. So when you look at this one, the top view, you will see a circle. So for helix, top view, circle. Now, when you take a look at the top view, you don't see z-axis. You do not see the progression of the helix up or down. All you see is xy, coordinate plane, and all you see is a circle. You learned the equation for the circle in parametric form as r cosine t and r sine t for the counterclockwise oriented circle. Now I need to go up in a z direction to accommodate for this constant rise. So the equation for this one is r equals r of t equals whatever your radius are. I'll put, let's use capital R, would be r cosine t, r sine t, and then let's say just linear t to go up. Can you have t squared? Sure. Can you have e to the t? Sure. Right? You can have other functions for that t, and it will either rise nicely, rise faster, rise really fast, right? For the e to the t, it starts winding nicely and then just shoots up quickly. And I hope we understand why helix equation is this way. So now when you see the eagle or a hawk, right, hunting, and they make those circles and then they strike, well, that's a helix. That's the helix path. Vector valued functions are oriented in a direction of increasing t. Vector valued functions are oriented in the direction of the increasing value of t. This is extremely important for your chapter 17. You will need to know the orientation as well. And all of the definitions and theorems will mention that you need to have counterclockwise and so on. So curves are oriented in space, and we can use them to use the orientation to see which way the particle or whatever is moving. Another cool curve that you can consider would be a slinky. If you connect two ends of a function together, you create, so you take, you know, the slinky, right? Now, connect the two ends and make a slinky donut. So it's going to be or take a helix and just bend it into a circle like a donut, and you will get the slinky. So slinky is going to go around, and an example function would be, let's say, r of t is equal to, in this case, three plus cosine 15t times cosine t, comma, 3 plus cosine 15t times sine t and sine 15t. And if you are to graph this, you will get the image in the middle. The image in the middle, you see that it's like a helix that it's bent into a donut, mathematical called torus. And we only focus on the red line. We don't care about the blue outline. Right? The blue outline is like a guide for us to wind this wire. So you can use Mathematica to graph this in 3D environment. And I think that's it, because I'm going to talk about limits of vector-valued functions in the next lecture, which is calculus of vector-valued functions. So let's take a look at another example. So vector, yes. Oh, by the way, when you are working on examples in a textbook, anytime you see that blue T, it stands for use of technology. They're expecting you to use either Mathematica or whatever to actually graph or do calculations, because they are not all of the calculations in Calc3 are pleasant, especially when you run into elliptical integrals, PhD level. So practice examples. They want you to find the line which is intersection of two planes. We did talk about two planes intersecting at the line. Look at the corner or on any of the corners that we have in the room. I mean edges, right? So you have the z-axis over there, which is between these two walls, or you can take a look at the ceiling and the wall, and there is a line, right, where they meet. So this is problem 12. So they're asking you for the R of t, which is intersecting line for 2x plus 3y plus 4z equal to 7. And the second plane is 2x plus 3y plus 5z equals to 8. How do we find the line of intersection if we have two planes? Yeah.
You set both of those equations equal to 0 and then set them equal to each other to find where they coexist.
What do you mean?
I don't know. So what I did is because I noticed like that you have the same coefficient for x and y.
Okay.
I subtracted from the first one. I subtracted 7 from each side. The second one I subtracted 8 from each side. And because both those equations equal to 0, I set them equal to each other. And then I got the equation z equals 1, which is what I was guessing the line, what the line was. Say r sub t is 0, 0, 1, which is 0, 0, 1 t.
So 0, 0, 1 is a point, right?
0, sorry, 0, 0 t is what I meant to say.
0, 0 t.
Yeah. But I didn't find I don't know how, because I should have gotten initial value points.
Yeah. All right, let's keep ticking. Because once we're done with this problem, we take a break. It's okay to talk with people around you. That if they're interesting, obviously, or something. If you find them interesting. So I'm just going to ask a question because I see you guys are staring at this. This is our first plane, my keyboard that I ripped off of the tablet. And this mouse pad is the second plane. And they meet at whatever angle, but they have this common edge. So what did we learn before? I believe we did a problem like this already. What do we need to do to find the line that they both share? What is the direction? How would you find the slope of this line?
Finding the angle.
How would you find the slope?
Cross product of the normal vectors.
There we go. Cross product of the normal vectors. Each one of these planes is described by its normal vector, which are these 2, 3, 4 and 2, 3, 5. And when you cross those two, you will get the vector v for your line. Then you have to find a common point and then put that vector through the point. All right, keep thinking. So how do we find the common point? We need that x0, y0, z0. And now we have v. So as soon as we find that x0, y0, z0, we can just write the vectors. So what do you think? Yes?
We set the equations equal to each other.
Okay, and get what? That's the same as saying subtract the equations, right?
Mm-hmm.
So I get z equals to 1.
Yeah. So would your answer be that 0, 0, 1 is the common point?
Is 0, 0, 1 even on these planes?
No.
No. We need to find any point that is going to be on these two at the same time. So we know that these intersect, right? Right? So if they intersect, then, and they have, these are polynomials, right? They have infinite domains in each way, each direction. Can't we just assign values for x and y, and then find the z so that, assign value, let's say, for x, and then solve the system to find appropriate y and z. So, to get the point, on the line. Let x equals 0. Solve three y plus 4z equals to 7. 3y 5 plus z equals to 8. When you subtract, you get z equals to 1. Now, if z is equal to 1, then y is also equal to 1 when you plug it back, right? So we subtracted. So 3y minus 3y is 0, 5z minus 4z is z, and 8 minus 7 is 1. We got this by subtracting. Then you take z, plug in, and get y equals 1. So the point that it's on both planes is 0, 1, 1. That's one of them. There are infinitely many, obviously. It's a line, right? So this is one of the points that it's on the line. We can check this by plugging in 0, 0, 0, 1, 1 in both of these equations. So 0 will knock this out. 3 plus 4 is 7. 0 will knock this out. 3 plus 5 is 8. Great. So this point does satisfy both of these, which means it lies on the line that it's between these two. So now I can just use x, y, z as 0, 1, 1 plus 3t minus 2t plus 0t. And then to answer the question that they asked is, what are the vector valued functions? So it will be 3t, 1 minus 2t, comma 1. So this is the line of intersection between these two planes. Let's do one more because we can. Graph r of t equals two sine t t 4 cosine t. What should this be? Think about it, and then figure out how to graph it. So any ideas what this might be?
Elliptical helix.
Excellent. Keep talking.
Centered around the y-axis.
Excellent. This helix is elliptical, so it's squished because we have two different radii, and it's also wrapped around the y-axis because that's where the T is. So to graph this, we would wrap it around the y-axis. So for the x-axis, we're going to keep 1, 2, 1, 2 units. Z-axis will have 3, 4, 1, 2, 3, 4. And it's going to be a little bit awkward, but it's going to wrap on the y-axis because that's where this function is. Now, if this function is a sine or cosine, it would be a slinky, right? It will wrap around. Right, so next time you see a little kid playing with us, right, the slinky, stop the kid, take the slinky away, and explain all of the mathematics of it, because now you know. Break time.